Hello, and welcome to Linear Algebra. This is lecture 17, and today's topic is dimension. So last time, we talked about bases and linear maps. Right, so remember, a basis is a linearly independent spanning set of a vector space. And we saw that the behavior of a linear map on a basis determines that linear map entirely. So we proved that, for example, a linear map is an isomorphism if and only if it sends a basis to a basis. This time, we're going to be talking about dimension. So we're going to be talking about the size of a linearly independent spanning set. Right, so, and I say that because last time we proved that if you have a set of vectors, say v1 through vm, w1 through wn, inside a vector space, and you know that v is the span of the w's, sorry, of the v's, and you know that the set of w's is linearly independent, then m is greater than or equal to n. Right? You need to have at least as many vectors here for them to span as you have vectors here that are linearly independent. Right? That's not to say that any set of m vectors is going to span. It's just that if you have a set of spanning vectors, you have to have at least as many as you have in a linearly independent set. So from there, it follows that any two bases of V must have the same number of elements. We call this number the dimension of V. Okay, so for example, the canonical basis or the standard basis of Fn, right? These are the vectors E1 through En, has n elements. So the dimension of Fn is equal to n. Okay, just like we expected, right? The dimension of R3 is 3. It's another example. Let's denote by Pn of R the polynomials of degree at most n with real coefficients. Right, this has bases, so the list 1x up to x to the n is a basis with n plus 1 elements So the dimension of P and of R is n plus 1. Right? Polynomials of degree at most n form a vector space of dimension n plus 1. Okay. Note that for a matrix of size m by n, the dimension of its column space CFA. Okay, so remember so the column space is the number is the span of the columns of the matrix, and its dimension is equal to the number of pivots in any row echelon form of A. And so that's because the columns that have a pivot you can use to write the columns that don't have a pivot, right? The free variables, the columns that correspond to free variables, right? So every non-zero entry in one of those columns occurs in a row that already has a non-zero entry before that in the reduced row echelon form. And so you can use the columns that have the pivots to write the other columns as linear combinations. Of course, that's after you've taken the reduced row echelon form, but row operations don't change that fact. And so the dimension of the column space of the original matrix is the same as the dimension of the column space of the reduced row echelon form of that matrix. So it's just the number of pivots. Now, clearly, if we're in the same situation we were at the beginning, where we have a bunch of v vectors and a bunch of w vectors inside a vector space, and v is equal to the span of the vectors v's, and the w's are linearly independent, then n is less than or equal to the dimension of v is less than or equal to m. Right? So at the beginning of the class, we recalled something from the end of last class where we showed that m was bigger than or equal to n, right? But now, because this is true every time you have a spanning set and every time you have a linear independent set, the dimension has to sit in between them, right? Because if you take a basis, then you could play it off against both of these to get these inequalities. Okay, so here's an interesting fact. Let's say that U1 and U2 are subspaces of V. And let's say the dimension of U1 plus the dimension of U2 is bigger than the dimension of V. Then U1 intersect U2 is not just a zero vector. Okay, so this is interesting. Why is it interesting? Well, because in math, it's really strong when you can say that something exists, right? So lots of theorems in math are like, well, if these things happen, then this thing happens. And so it's like a bunch of dominoes, right? If this domino falls, then the next one has to fall. And that's great. But you really need existence theorems sometimes to get the dominoes started, right? To say that there's something, right? Because knowing that if this domino falls, then the next one falls is not really so useful if you don't show that the first domino falls. So existence theorems are great, and also because the often in the axioms you might have like a distinguished element, like fields have to have zeros and ones, and vector spaces have to have a zero vector. But that's it. You might not have anything else. And so the axioms themselves are not going to provide elements for you. They're not going to provide existence. So it's really strong when you can prove an existence theorem. And in lots of fields, especially when you go to analysis, things like that, every time there's a new object, then you want to know, when can I prove existence? Okay, so this is an interesting theorem because it shows that you have non-zero vectors, and you get these non-zero vectors from a very weak information. All you need to know is that the sum of the dimensions is bigger than the dimension of the space that you're looking in. Okay, now to prove this, let's check the contrapositive. Right, so instead of showing that this implies this, we'll show that if this fails, then this fails, right? And that's an equivalent statement. So here the contrapositive says that if U1 and U2 are subspaces of V, such that the intersection is just the zero vector, then the dimensions add up to at most the dimension of V. Okay, so let's prove this. Okay, so I want to prove an if-then. So I should focus on the then, right? So this is what I want to prove. So I need to figure out how to get this statement out of the hypotheses that were given. Okay. So I want to prove something about these dimensions versus this dimension. And the dimension, by definition, is the size of a basis. So what I should do is take a basis of this guy, take a basis of this guy, compare it with the basis of this guy. Okay, so let's say V1 through VP be a basis of U1, and let's say W1 through WQ be a basis of U2. Right. I want to show that this is less than or equal. So P plus Q is less than or equal to the dimension of V. So thanks to the lemma from last time, will be done if we show that the list where you take the V's and include the W's, if we show that this is linearly independent, then we'll know that its size, P plus Q, is less than or equal to the dimension of V. Okay, and that's what we need to show. So let's check that this is linearly independent. Okay, now as we said last time and times before that, every proof of linear independence starts the same way. To show that this is linearly independent, assume that you have a linear combination. Let's call it some AJVJ plus some BJWJ. Well, let's use different dummy variables. So BK, WK, K goes from 1 to Q. Assume that this long linear combination is equal to 0. We need to show that AJ is equal to 0 for every J and BK is equal to 0 for every K. Right? Every proof of linear independence starts the same way. You have a set of vectors. You want to show that they're linearly independent. Take a linear combination, assume that it's equal to 0, and prove that the coefficients have to be 0. Okay, so we need to show that all of these coefficients are equal to 0. What do we know? We know that U1 and U2 are subspaces and that they intersect only in the 0 vector, right? The only vector that is both in U1 and in U2 is a 0 vector. Okay, I want to use that information. So I have this, and I want to use the only vector in both U1 and U2 is a 0 vector. Now notice that this is a vector in U1, and this is a vector in U2, right? Because this is a basis of U1 and this is a basis of U2, right? So if their sum is equal to 0, that means that one of them is equal to minus the other one, right? So from, right, let's give this a name. Let's call that star. From star, I can write the sum of the AJ VJs is equal to minus the sum, K goes from 1 to Q, of BK WK. Okay, now this is obviously in U1, and this is obviously in U2, as we said. But if a vector in U1 is equal to a vector in U2, then this vector is also in U2, and this vector is also in U1. So both sides of this equality are in U1 intersect U2, but U1 intersect U2 is the 0 vector, just the 0 vector. So thus we know that the left-hand side is equal to 0, and we know that the right-hand side is equal to 0. Okay, but the VJs are a basis, and the WKs are a basis, right? The VJs are a basis of U1, WK is a basis of U2, right? And because they are a basis, they are linearly independent. So if you have a linear combination of the VJs equal to 0, then the individual coefficients have to be 0. And same thing over here. If you have a linear combination of the WKs equal to 0, then the coefficients have to individually be equal to 0. So we get the AJ is equal to 0 for every J, and BK is equal to 0 for every K. And that's exactly what we wanted to show. Okay. Wonderful. So dimension is very useful in that it gives us existence. If we have two subspaces of a vector space and the dimensions are too big so that the sum is bigger than the dimension of the ambient space, then the subspaces are too big to not intersect beyond 0. They have to intersect in something greater than 0. Okay, But so that's great, and that's a wonderful use of dimension. But the most important use of dimension is that if all you care about from a vector space is its vector space structure, right? If you can't tell the difference between isomorphic vector spaces, then among finite dimensional vector spaces, the only thing you notice is the dimension, right? So what I'm trying to say is that the dimension is the only thing that distinguishes finite dimensional vector spaces up to isomorphism. So let's write that down. It turns out that the dimension is the only thing that distinguishes finite dimensional vector spaces up to isomorphism. Right, so as a theorem, let V and W be finite dimensional vector spaces over the field F. V and W are isomorphic if and only if the dimension of V is equal to the dimension of W. Okay, so up to isomorphism, the only thing that distinguishes is the dimension, right? Why do I keep saying up to isomorphism? Well, sometimes you care about the vector space beyond its vector space structure. For example, we saw way back when we started talking about linear maps that for any field F, F4 is isomorphic to the 2x2 matrices with coefficients in F, right? So of course, notice the dimensions work, right? The dimension of m by n matrices is m times n. The dimension of Fn is n. And so F4 and 2x2 matrices with coefficients in F have the same dimension. However, sometimes you want to think about F4 as being column vectors, and you want to like try to make pictures and stuff, and you want to think of 2x2 matrices as being things that come from linear maps. So you care about more than the vector space structure, right? Okay, but this theorem says if only the vector space structure matters, then only the dimension matters. Okay, let's prove this. Okay, so again, we want to prove an if and only if. So that means we need to check that this implies this, and vice versa. This implies this. Okay, so let's go with one way. So in this case, we're going to assume V and W are isomorphic. We want to show that the dimension of V is equal to the dimension of W. Okay, so what does it mean for V and W to be isomorphic? It means that there exists an isomorphism between them, right? So our assumption is that there is a map, a linear map between V and W that is an isomorphism. Okay, wonderful. So what do we want to show? We want to show the dimension of V is the same as the dimension of W. What's the dimension? The dimension is the number of elements in a basis. So we want to show that the number of elements in a basis of V is the same as the number of elements in a basis of W, right? What can we use? We can use that there is a map between them that is an isomorphism. Okay, but we proved last time that isomorphisms are precisely those linear maps that take a basis of V and send it to a basis of W. Okay, so pick a basis of V. Let V1 through Vn be a basis of V. Since T is an isomorphism, T of V1 through T of Vn is a basis of W. Hence, N is equal to the dimension of V and to the dimension of W, right? Which we're going to show. So let's use a check mark because we've proven one direction. Let's prove the other direction. Okay, so for this direction, we get to assume that the dimensions are the same. We want to show that the vector spaces are isomorphic. Okay, so assume dimension of V is equal to the dimension of W. Want to show V and W are isomorphic. Okay. So another way of saying this, assume that every basis of V has the same number of elements as every basis of W. We want to show that there exists an invertible linear map from V to W. Okay, so let V1 through Vn be a basis of V, and W1 through Wn be a basis of W, right? So our assumption, equality of the dimensions, tells us the same number of elements here. Okay, now we've seen last time that given a basis of V, I can specify a linear map by deciding where to send each element and then extending by linearity. So let's define T, linear map from V to W, by requiring T of Vj to be equal to Wj for every j, and extending by linearity. Okay, so we have a linear map. Now, our theorem from last time was that a map is an isomorphism, a linear map is an isomorphism, if and only if it takes a basis to a basis. This is a linear map, and it takes this basis to this basis. So it has to be an isomorphism. Since T sends the basis V1 through Vn to the basis W1 through Wn, it is an isomorphism, which is what we wanted to check. So now that's both directions. Okay, in particular, every finite dimensional vector space V over the field F is isomorphic to Fm with m equal to the dimension of V. Okay, so if for every given dimension there is only one vector space up to isomorphism, then we can use our favorite vector space of dimension m to represent it, right? So every vector space of dimension m is isomorphic to Fm. And how do we get this isomorphism, right? Well, directly from this proof, you pick a basis, right? So if you give me a vector space of dimension m, then I can identify it with Fm every time you give me a basis of V, right? Every basis is going to give us an isomorphism to Fm. In fact, we'll see that different bases give us different isomorphisms with Fm. So you can think of a choice of bases as giving you coordinates on your vector space. And those coordinates make it look like Fm. But if you were to pick a different basis, you're changing the coordinates. So you have the same vector space, but you have different identifications with Fm. Okay, we'll spend a lot of time thinking about that. Okay. Here is another consequence of the lemma from last time. If the dimension of a vector space is m, and V is equal to the span of m vectors, v1 through vm, then actually those vectors, put them into a list, and then you get a basis. Now remember that for bases, we want to think about ordered sets. So we call them lists. So a basis always comes with an order. And indeed, we have shown that any list of vectors that spans V contains a sublist that is a basis of V. So remember, this was an algorithm we gave where you gave me a set curly B. No, you gave me a set that spanned V, and I constructed a set curly B that not only spanned V, but was linearly independent, and hence was a basis. So we saw that any vector space that has a finite spanning set is actually finite dimensional. That's the definition of finite dimension, sorry. We saw that any set that has a finite spanning set has a finite basis. In this case, since a basis has exactly m elements, it must be the whole list, right? So if this set spans V, then we checked by an algorithm that there is a subset that spans V and is linearly independent, right? But that makes it a basis, and we know that every basis has m elements. So that means that you can't lose any of these elements. So they must already be linearly independent, right? So if you have a vector space of dimension m, and you can span it using exactly m elements, then those m elements have to be linearly independent. Okay, so now let's show like the other way around. Instead of starting with a spanning set and then shrinking it to get something that's linearly independent, let's show that if you start with something linearly independent, you can always expand it until you get something that is linearly independent and a basis, and a spanning set. Okay, so theorem. If V is finite dimensional, and B inside V is a linearly independent set, Well, let's make it a list because I want to make it into a basis. Then B can be extended to a basis of V. Okay, so if you have a linearly independent set inside a finite dimensional space, then you can always add elements until you staying finite linearly independent until you span all of V. Okay, and that is basically how we're going to prove this. So let's write B. So let's give things name. Let's let the dimension of V equal M, and let B be the list V1 through Vn. Right? So necessarily, N is less than or equal to M. Okay, so now if the span of B is equal to V, then N is equal to M, and we're done. Otherwise, V is bigger, strictly larger than the span of B. So we can pick Bn plus 1 inside V minus the span of B. And add it to B. Note that B is still linearly independent. It's still linearly independent by our linear independence lemma, right? Because the linear independence lemma says that the new set B, where we've added Vn plus 1, is going to be linearly independent because no element can be written as a linear combination of the ones that come before it. Okay, now we iterate. Iterating, we keep adding elements until B has length dimension of V, right, which is M, at which point it will be a basis, right, which is what we wanted to show. So even simpler than our algorithm that started with a spanning set and removed elements until we had a basis, we start with a linear independent set and we keep adding elements until we get a basis. Okay. Next, let's prove this theorem, which says that dimensions and subspaces behave sort of how you would expect. So if V is finite dimensional, and U is a subspace, then, okay, U is finite dimensional, the dimension of U is less than or equal to the dimension of V, and if the dimension of U is equal to the dimension of V, then U is equal to V. Okay, so this behaves just like you would expect. If you have a subspace, well, then it's going to be smaller than V, right? So what do we mean by smaller? Well, it's not going to be infinite dimensional. In fact, its dimension is going to be bounded above by the dimension of V. And should it equal the dimension of V, then in fact, it's the same space, right? You can't put you can't find a three-dimensional subspace of R3 that isn't all of R3. Okay, so let's prove this. Okay, we want to show that U is finite dimensional. So finite dimensional, remember, means that there is a finite spanning set. Okay, well, let's see. If U is just a zero vector, then we're done. It is finite dimensional, it's just the dimension 0. Otherwise, pick U1 inside U, excluding the zero vector. If U is equal to the span of U1, then we're done. Otherwise, pick U2 inside U minus the span of U1. Right? And note that the list U1, U2 is linearly independent. Okay, now we keep going, continuing in this way. We build successively larger linearly independent sets, subsets of U. The size of these sets is bounded above by the dimension of V. So the process must stop after finitely many steps. At that point, the linearly independent set must also span U. Okay, so just by picking vectors in this way, we're guaranteed to find a basis of U. Okay, so that proves one, a finite set that spans U. So U is finite dimensional. Okay, 2, we want to show the dimension of U is less than or equal to the dimension of V. So, well, if U1 through UN inside U, which is inside V, is finite dimensional, is linearly independent, then N is less than or equal to the dimension of V, right? So in particular, this is true for any basis of U, it has to have fewer elements than the dimension of V. or as many elements as the dimension of V. And then finally, if in part 2, n is equal to the dimension of V, then this set must be a basis of V. Right? So the basis of U is a basis of V, and so V is the same as U. That's what we wanted to show. Okay, so that tells us this theorem, which seems very obvious, it should be very intuitive, tells us, for example, that every subspace of R3 must have dimension zero, 1, 2, or 3. So the subspaces R3 are either the origin, a line through the origin, a plane through the origin, or all of R3. Okay, so this intuitive fact that we used early in the semester is now entirely justified. Those are the only possible subspaces you could have sitting inside R3. Okay, and we'll stop there for today and pick it up there next time.